Okay, let's look at something here. The last part of this section, it's a big section. The work you do is pretty easy, but understanding why this works is the part that's just a little bit tougher. Before we jump into this, any questions? I'll throw open an opportunity here for some questions on assignments. Anything we need to look at? You want me to pull up real quick? Should I just pull up the assignments? And wanted to do this. Okay, so what about stuff? I mean, I'm not going to go through these problems. I want you to get some practice, but you get the idea. These are just first fundamental theorem, or fundamental theorem of calculus. After today, we'll call it the first fundamental theorem, where you're just trying to, what's the whole point here? Adding up an area under a curve, right? So the integrand, so here's the function under which you're calculating, underneath that curve, you're calculating the area from 0 to pi fourths. And the trick, remember, is just you find the antiderivative and then evaluate it from 0 to pi fourths, right? And I think most of the questions on this assignment are pretty similar to that. These are trig ones, so you got to remember your trig integrals. Those are out of the book based on the areas. Do we want to go through an example of one of those, something like that, or okay? Let me pull one up out of the book. So what about draw? Yeah. Okay, I like these. Whoops. What about? Okay. Okay, what about that? Zero to 2, okay. And let's look at why that is. So if I were to do, and this is going to be I'm not going to make this an accurate sketch at all, right? But one thing we do know, if I took this function up here, if I evaluated at x equals 0, where is it? So let's make this function blue. When x is 0, y is 0, okay? When x is positive, y is positive. When x is negative, right? That'd be negative, wouldn't it? Right? Because both of those players would be negative. So it's going to be something like, what's it really going to look like? Something like It's going to be slightly stretched out like that a little bit. And then y equals 0 is just the x-axis, right? And then x equals 2 is just over here at 2. It's like that, isn't it? So what's the only area that's bounded by all three of those? Yeah, just that little sliver in there, right? Okay, so how are we going to set that up then? We want to find that area. What do we do? Okay, so we're going to, well, we'll take a definite integral, right? Because we're going to have limits of integration. So we're going to have to take a definite integral of the function, right, that forms the top of the area. So that's just that guy, right? From 0 out to 2, right? Because x is the variable of integration, right? That's our independent variable, okay? We can, by the way, we'll do just a couple examples of this year, not a ton, but we could also do integrals sideways too. We could let y be the variable of integration, and then what would that look like? I mean, just one quick example for now, and we'll look in more detail later, just so you make this connection. Like if I wanted to, what if I wanted to find the area in a sideways sense, under the sideways parabola, x equals y squared, from y equals -1 to +2. What's that going to look like? So if I'm reckoning my area now as area under a sideways curve as a function of y, under now instead of meaning from the function down to the x-axis must mean from the function over to the y-axis, yeah. So we'd be adding up this area, wouldn't we? Right? Okay. And by extension, what do you think that integral would look like if I wanted to add up that area? The integral of what? This time, instead of writing y equals f of x, this time I've written x equals f of y, right? What do you think? What's going to go in the integrand?
Y squared.
Y squared, yeah. What's going to go out there? dy, exactly. And it's going to go from, there you go, right? It would work exactly the same. The math would be the same way you do the math normally, just a little different picture, right? Okay, but for ours, we got this guy. So let's finish this one up. The one we're doing currently. Okay, so how do we do this? Just a quick review of fundamental theorem. Yeah, just take an antiderivative term by term. I don't even have to split it up, right? I can just, what's the antiderivative of x cubed?
X to the 4th.
Yeah, x to the 4th over 4 plus
X squared over 2.
x squared over 2. And I can evaluate this either piece by piece or as a whole. I can evaluate it from 0 to 2. I might as well just do it this way, right? Because this is a really convenient one. What's the value of that expression going to be at 0?
0.
0. Yeah, so I'm just going to get, if I plug 2's in, I'm going to get 2 to the 4th over 4 plus 2 squared over 2 minus 0. And what's that give me? 16 over 4 is 4 plus 2 is 6. Did I do that right? So I get 6 is my area. Okay? No biggie. All right, what about, let's look at the next assignment. What's that? Oh, do you want to do a trig one? Okay. We can do a trig one. Trig's fun. Let's do, okay. How about this? Okay. Okay, what about that? So we got to think, did I give you guys the sheet with the integrals on it? Antiderivatives? Yeah, I'll print it out. It's on the site, I'll print it out to you. But you can just think backwards on these. If you know the derivatives, you know the antiderivatives. So play calculus, Jeffrey. The derivative of what is secant theta tangent theta? Secant theta, right? Okay, so we know that if we can pull that 4 out front, we don't need that inside. And so this is going to look like 4 times the antiderivative of secant theta tangent theta is secant theta, and we're going to evaluate that from negative pi thirds to pi thirds. We'll look back on this in, well, that's all right. Well, maybe we will. Let's see. So what do we get then? Say it again. Did I mess something up? No. Okay. So we're going to evaluate this from negative pi thirds to pi thirds. So first we've got secant of pi thirds minus secant of negative pi thirds, right? What's secant of pi thirds? Think unit circle. So pi thirds is up there, right? What are the coordinates at pi thirds? It's over small, up big, right? So what's that?
Square root of 2 over 2.
No. Right? You can do the little hand trick if you want to. Right? So you know that's going to be this one right here. Right? So you get the square root of 1 over the square root of 4, right? Which over 2, which is just 1/2. Does that make sense?
Yes.
And then you're going to get down here for the y coordinate, you're going to get the square root of 3 over 2.
Because it's always over 2.
It's always over 2, yeah. Right, so that's how you know it, right?
Oh.
Just make it a little shorter.
1/2 square root of 3 over 2. Right? I showed that to you.
Yeah, you did. We just forgot it.
I just
Yeah.
don't understand. Yeah, why did we pick this finger?
Why did I pick? Oh, because look, so that one goes there, that one goes there. This is going to be pi 6, pi 4ths, pi 3rds. Right? Those are the 3 points. So that's the one that goes down.
Yeah, I know.
Because it's always the square root of the number of fingers there, right? So I get the square root of 1, which is 1, over 2. It's really cool, right? Square root of 3 over 2. Now what if it were this guy? Then we would go square root of 2 over 2, square root of 2 over 2. Right? You like that? If I do this one, square root of 3 over 2, square root of 1 over 2. And if I do this one, square root of 0 over 2, which is 0. And then square root of 4 over 2, which is 1. So it'd be 0, 1, right? You like that? Ooh.
Square root of 1.
Yeah. Okay.
I've got 3 fingers.
So that's good.
This one.
Do what you like, that's fine. So then the x coordinate's 1/2, the y coordinate is square root of 3 over 2. So secant is the reciprocal of cosine. So cosine is the x coordinate, right? So it's going to be the reciprocal of 1/2, which is 2. Okay?
Because that's square root of 1. square root of 1.
Now, what about the secant of negative 1/3? So negative 1/3 is going to be down here, right? So the x-coordinate's the same, isn't it?
It's just
Right? So I'm going to get 2 minus 2, right? Because negative 1/3 is down there. The coordinates are going to be 1/2 negative square root of 3 over 2. But secant is the reciprocal of cosine, which is still the same for both of those. So I'm going to end up getting 2 minus 2 is 0. Can anybody tell me how we could have avoided even doing all that work?
Pi is negative 5/3.
Okay, but you know, we have to, so if we have an integral over symmetrical limits, if it's an even function, so let's review those two little theorems, because they're useful, especially the odd one. For an odd function,
It's just
the integral from negative a to a of f of x dx is 0 always, right? For an even function, the integral from negative a to a of f of x dx is just 2 times the integral from 0 to a. Which actually makes it easier, right? Because then you get to use 0 as the limit. Okay, and the classic example, the one we looked at in class, just a quick review, is this guy, right? If we use, for an odd function, we'll just use x cubed, right? So, looks like that. And so if we go from there to there, I get as much positive area there as I get negative area there, so they always cancel, right? For an even function, like x squared, if that's negative a and that's a, well, I get the same amount of area there as I get there, so why not just double that, right? Then I get to use 0 in my limits, which it makes it easier, okay? So all we'd have to do here is just show that that's an odd function. Okay, so how would we do that? 4 secant theta tangent theta. F of theta equals 4 secant theta tangent theta. What's my test for an odd function?
negative theta. If you have a negative theta.
So if I plug in a negative value for the argument, for the variable, I get back the opposite of f of theta, right? So we'd have to show that f of negative theta equals negative f of theta, right? Well, what's that give us? If I plug in, let's see what we get. 4 times secant of negative theta times tangent of negative theta, right? Let's do this in terms of sines and cosines, how about it, right? So secant is 1 over cosine, tangent is sine over cosine, right? So we'd end up with 4 sine negative theta over cosine negative theta squared. What can you tell me about the bottom for sure?
it's always going to be 4.
Yeah, because I'm squaring it for one thing, right? So I'm going to get back on the bottom, cosine of negative theta squared is equal to cosine squared theta, right? Because I'm squaring it. Okay. What about the top?
That will become negative.
It's negative sine theta, isn't it? Think about a sine curve. You could either think of it in terms of, it's a property. You guys remember those properties from last year? Sine of negative theta equals negative sine theta. Cosine of negative theta equals cosine theta, right? But you may not remember those, but it's easy to think of in terms of a picture, right? If we look at this on the unit circle, think what this means on the unit circle. If I'm going over to positive theta or back to negative theta, sine is the y-coordinate, isn't it? Right? So if the coordinates here are x, y, what are the coordinates there?
Also, you say class.
X, negative y, right? See what I'm saying? So the sine of negative theta is the opposite of sine of theta, isn't it? Right? Cosine would stay the same though. The x's stay the same, right? You can think of it in terms of a sine graph too if you wanted, right? Here's what a sine graph looks like, right? So if I go over positive theta and back negative theta, well, look what happens. The y values are opposites. Okay? See what I'm saying? So, what's that tell us then? So we end up with 4 over cosine squared theta, but I get times negative sine theta. Let's pull the negative out front with the 4. And so I get negative 4 sine theta over cosine squared theta, which is the same thing as negative 4 secant theta tangent theta, right? So it is an odd function. That's a lot of work to do. It's a lot of work to do. But you could have thought of this maybe more easily by just saying, what about the behavior of secant by itself and tangent by itself? Secant is 1 over cosine. Cosine's even, so secant's even, right? Tangent is sine over cosine. Sine is odd and cosine is even. What's the result of dividing an odd function by an even function? It's odd. Yeah. Right? So you could just kind of think through that one and know right away, okay, I'm getting an even behavior times an odd behavior, which is an odd behavior. So I know it's going to follow that rule. I'm going to get 0. Okay? In this case, I don't know, probably easier just to do the integral. But if this were a really hard integral to do, it might be worth investigating it like that to avoid having to do the calculus, right? Okay? All right. So let's do one mean value theorem one too. If we don't get to new stuff today, we'll start it. We'll just barely start it.
And then one time she was like, "Can I switch out?" I was like, and the next day
Okay, real quick, how are you going to find the shaded region on the right? This region. How are you going to do that one? You're going to find the area under that curve.
And the area from 0 to 2 is y equals 4x squared.
Yeah.
And then 2 to 4 is y equals 32 by 6.
Everybody see that? You got to break it into 2 areas, which makes sense because it's a piecewise function, right? So because the curve changes, the integral is going to change. Good. Okay, how about that one? You want to find the shaded region there.
What number is after the x?
This is number 8, so I'll make it bigger. Can I stretch that up? I'd have to subtract, wouldn't I? Right? Now, so I would be looking at what area minus what area to get the shaded region. Okay, good. So the area under the blue curve minus the area under the red curve. Do you need calculus to find the area under the blue curve? No. That's geometric, right? That's just, what is that? Pi fourths times 2, okay, minus the area under the trig function from 0 to pi fourths. Good. Good. Okay. What's NINT? Do you know? Nint? It's nint. That's numerical integration. So you can either do that on your calculator. That's this stuff. When they talk about nint in a textbook or something, they're just talking about using
Your calculator.
using some numerical method. So not a human method. So it'd be that one, right? Where you just go math, right down there, number 9. And then you're just plugging in all the parameters, right? And it's going to give you back a numerical answer. Or you can do it graphically. Or on, what did we decide on Desmos? We could do it on Desmos too, didn't we? Didn't we do it? And we didn't see a way. Has anybody figured out how to actually have it shade the area in Desmos? I'm not sure how to do that, but in Desmos, you just go, remember on Desmos, if you just go down to functions, miscellaneous, there's your integral. So you can actually put in a definite integral, right? So the integral from 1 to 3 of x dx, and it gives me an answer, okay, a numerical answer. Okay, so that's handy too. So that's all that means. Oops. Go away. Okay. Then you're okay with stuff like that? Finding an average value of the function on an interval. How do we find average value? Mean value?
Didn't we find the area?
Area divided by, yeah, the width of the interval. Yeah, that's no big deal. Yeah, you're good. You got this stuff. All right. So what I want to look at today, let's look at something different. This is what's called an area function. Okay, what does this mean? What if I do something like what do you suppose that means? The book doesn't talk about these very much. It just shows you one little way to deal with derivatives. But I want to take a second and really just talk about what this is. This is kind of interesting. What if I were to graph that? I don't know what f is. F is just some generic curve, right? So if I were to graph this thing, what would it maybe represent? So here's f. And I'm going to call that A. A. What's the x? I mean, what's the t, first of all, I guess? T is literally, t doesn't get much respect. It's what we call a dummy variable. Okay, and it's really just there to define the shape of the curve. If I were to plug in input values, I want to know what the output values are so I can make a sketch. All right. Okay, what's x though? This would be the t-axis. What's x? X is the upper limit of integration, but is it constant? It's a variable. Right? It's a variable. So here's x, right there. That's x. And so this represents the area under this curve. But as x changes, what's that do to the area?
Expands or divides.
Okay, so it's gonna either make it bigger or smaller if it's under the x-axis, I guess, right? If x is going backwards, then it's getting smaller. But it's a function of x, isn't it? Right? So this is a real kind of thing. Sometimes we are interested in knowing what's the area as a function of x, or even more crucial, a lot of times we want to know what's the rate of change of that area. So let's talk about that for a second. What if I've got this area function that's defined by the shape of the curve, the lower limit, and the value of x, the variable value of x. But what if I want to know at what rate is that changing? Okay, so what is the derivative with respect to x of, well, a of x. Okay? Think about that for a second. Right, so that's going to look like, if this is a of x, it's going to look like the derivative with respect to x of that integral, right, with a variable upper limit. What are the things that are going to impact the rate at which the area is increasing?
Slope?
The slope, yeah, the slope will. Indirectly. Is the area going to be, it's going to depend on how fast x is sweeping out area, right? How fast x is moving. Agreed? The faster x is moving, the faster area is increasing, right? But what if like x was right there compared to, call that x1 and that x2? Which value of x, if x is sweeping out area at a constant rate, if x is changing at a constant rate, for which one of those two values of x is the rate of change of area going to be larger? Now just imagine I'm sweeping out area here, so I'm going from there to there. So I just increase my area by that little amount. How come over here?
Because
The
the
slope is
value of
much greater.
Okay, because the height of the area is determining the, that component of, or that dimension of the area is much bigger. I'm only going to sweep out area, the same amount of area in the same time increment, right? But here, when I sweep out that tiny time increment, I'm getting a lot more area, right, per second, let's say, than I am right there. So the rate at which I'm changing area, if I hold everything else constant, if I'm saying that I'm sweeping out area at a constant rate, it's really going to depend on the height of the function, isn't it? Right? If the function is twice as high here, or 3 times as high here as it is here, I should be sweeping out area at 3 times the rate here that I am there. Agreed? Does that make sense? So then what's the answer to this? The rate of change of this area function from a to at x, right? So from a to x. So we're at the point x. At what rate there am I sweeping out area? What's the answer? It's really simple. F of, you almost got it. F of x. F of x, right? It's going to be the value of the function at x, right? T is, think what, I mean, it's really hard to explain what T is. I've never found a good way to do it. T is just there. It's kind of like a bat's sonar, right? It's sending out, it's pinging the surroundings to just figure out what's this curve going to look like in the future, right? So we get a map of what the trajectory is, but x is going to be, x is a variable, but for a given value of x, there is a certain height to the curve, right? As x changes, the area is going to be swept out in such a way that the top of the area is determined by this shape of the curve, right? But for its given value of x, the rate at which it's changing is only going to depend on the height at that moment. See what I'm saying? We're not asking about the total area. We're just asking about the rate at which the area is changing. Area per unit of time, right? Or per unit of progression along the t-axis. See what I'm saying? So that's our answer, right? It only depends on the value of the function at that particular x value. Okay? You see what I'm getting at? So this is the very question. Yeah.
Is the only reason T's there because you don't want to have f of x twice?
Right. Yeah. You could actually write this with an x there. It would be, it's not ridiculous to do. It's just a little bit confusing because then, it de-emphasizes the fact that the variable here is really the upper limit of the integral and not just the generic input value, right?
Is this independent of whatever a is?
It is. Makes no difference, right? Because it's a good question because a could be, let's say a is positive 1 here. A could be -5, and it doesn't change the rate at which the area is changing. You see what I'm saying? Like, let's just say hypothetically that this area right there is equal to 1, and this area right there is equal to 3, the little incremental area that I'm adding. So what's the rate at which I'm changing area here? I'm changing area at a rate of 1 per unit t, right? Here I'm changing it, I'm adding area at a rate of 3 units of area per unit of t. It doesn't matter how much area I've already added up. I just want to know how fast am I adding or subtracting area. That's what this means, the rate of change of the area, not the total amount, right? If you're driving in your car and I've got the cruise set on 60 miles per hour, does it matter how far I've traveled? Makes no difference. The rate at which I'm changing distance is 60, right? Regardless of how far I've traveled on that day, right? Okay, so here's kind of our, what I'm going to call the book's weak sauce version of the second fundamental theorem of calculus. I'm going to give you a much better one. So, just this. The derivative with respect to x of, we just actually wrote it, f of t dt from a to x is f of x. Okay? How much time we got? 7 minutes?
Yeah.
Okay, that's enough. That's enough. Okay, now we're going to take this, we're going to move this forward, right? Hyperspeed here. We're going to do something different to this. We're going to take the same idea that we had before.
Oh, wait, sorry.
Yeah, want to go back?
It's the same thing you just wrote.
I know, I missed it 'cause I'm there.
Just to show you how easy this is, I mean, applying this is so simple.
Okay.
Like if I want to calculate, let's say we're going to define our area function as the integral from -11 to x of, I'll pick one you don't even know how to deal with yet, the natural log of t dt. What is
The natural log of x.
f prime of x equal to?
Natural log of x.
That's it. Okay, without even knowing how to do the calculus, the pattern works, right? You don't even know how to do this one analytically yet. You will, right? Okay, now would it work for, what if I gave you one, so what if I gave you one like this? I want to prove one more point. Maybe I don't want to delve into the next level today anyway. I might not finish. So let's just show that this works. What if we've got my area function is defined as oops. Okay. Let's actually solve this area function, because we can do that. So let's take this definite integral, in other words. What do we get? But I don't want to make that 7. Let's make it 0. Make it something convenient this time. So what's that equal to? I'll pull the negative out front, and we'll go from 0 to x, right? So I'm just going to get back negative cosine x minus cosine of 0. What's cosine of 0? 1. So I'm going to get what's that? Negative cosine x minus, so I'll do 1 minus cosine x, right? So that's f of x. I think I distribute my negative, right? Okay, well, let's do this the hard way, and let's calculate the derivative of that with respect to t. So what do we get? With respect to x, sorry. Derivative of 1 is 0. Minus, what's the derivative of cosine x? So f prime of x equals sine x. Okay, but a lot easier to use the second fundamental theorem, right? That's a little easier, right? Okay. I dropped my pen. Okay. You get it? A lot easier to do, okay? All right, so I'll just leave you pondering this, and we'll talk about this tomorrow. What if I did this now? What if we're going to calculate the area under F from A to X, but this time we're going to vary the rate at which we're changing X. So now we're going to define our area function as the integral of f of t dt from a to, let's say, x squared. So now think what I'm doing here. I'm adding up the area under the function f of t from a to x squared is defining the top of my limit. So this isn't really an x, it's an x squared, right? So when x is 1, what's x squared?
1.
When x is 2, what's x squared? 4. When x is 3, x squared is, you get the idea. So as I increase x at a constant rate, what's happening to the upper limit of my area function? It's increasing at a much faster rate, isn't it, right? So now there's two things affecting the rate at which area is swept out, right? I've got, one of them is obviously the height of the function at x squared, right? But the other one is the rate at which x is changing. See what I'm saying? So we got two things we've got to consider here, okay? Ponder that one for today, for tonight. And we'll pick that, how we're going to deal with that tomorrow, we'll pick that up.